given.
Right.
Otherwise, exactly. Exactly. Now, to Mark's question, well, if you're given the name, should I just make up a new one? Because this is already, you've seen it, right? How about if I make up a new one? Okay. Give me a second. I've got my fingers crossed that the name, okay, you know what, that's a learning experience too. When I'm trying to picture things in my head and trying to find a name just without drawing it, I do sometimes make mistakes there. But again, that's a learning experience. So, okay, how about this? Ooh.
But there you're giving it to us.
Well, you have to. Without the number, you can't.
Yeah,
How would you?
You can't.
But the question was if you've given us that,
Like
just the
Z, like just like Z.
Well, then you can't have more than one stereo center. As I said, okay. Fine, let's just do that. Okay, no carbons with 5 bonds, Sunita. Please don't do that.
You gotta don't worry, take your time.
Say again.
You gotta don't worry.
No, but too much pressure. You're all staring at me.
We'll look away.
we'll look to the other wall.
I'm staring harder.
You're what?
I'm staring harder.
He's staring harder.
Yeah, he wants to get back to me with all those Hawaii.
Yeah.
Absolutely.
Right? Yeah.
Count your fishing carbons.
Oh, can I have the last name? Because she erased it. Just want to make sure I have the right name for the last one.
Z chloro.
A chloro. 7. Ethyl non-6.
No, don't do that. Sorry.
Thank you.
Okay, let's try this. Hopefully the name is correct for the structure. But what's the parent? So here's the thing, the question that I think I got from you, Mar, there's no number here, right?
Yeah.
Okay. What part of this name can actually be E or Z? Can this be E or Z?
No.
So only the alkene can be E or Z, right?
Oh, there you go.
But yeah, only alkenes are E or Z, nothing else is E or Z. Of course, there are 2 alkenes, so we have to figure out, okay, which one of them, because there's only one, the other one doesn't have E or Z, otherwise that would have been listed. So we have to then draw the structure and figure out which one would have to be Z. Make sense?
Yeah.
Okay. I think, Kerry, what I understood, your question was, what if these numbers weren't given? That's not possible. That means that the name is incorrect, because how are you to know? Absolutely. Okay, let's try and draw this, please. Go ahead, give it a shot. Yes, please.
Do you have, is the reason why the 8 is in front of the 3, is that on purpose?
Yes.
Oh.
That's on purpose because there are 2 of those. If there is more than one of either double or triple bonds, you've got to include that A.
No, I meant the number itself. Like,
8.
the number 8 is in front of the 3, is that on purpose?
Ah! Thank you. Thank you.
I'm just figuring it out.
Is that better? I think that might work out, yeah. Yeah, how can you have 8 if there are only alkenes starting at 8 if there are only 8 carbons total? Yeah, not possible. 7, let's make it 7. Yeah, let's give it a try then. Now once again, stereochemistry also has to be shown. if that's included. If it's not included, then you don't have to, or it doesn't matter. But if it's included, you've got to be careful. So what's the parent?
Octenine.
So 8 carbons, right?
Yep.
Mm-hmm.
2, 3, 4, 5, 6, 7. But then there is a triple bond on 1. Everybody okay? 1, 2, 3, 4, 5, 6, 7, 8. Right? Where are the enes?
At both ends.
So 1, 2, 3. So there's an ene here.
Uh-huh.
Free.
And 4, 5, 6, 7. Right?
Uh-huh.
So, and where are the 3 bromo? 1, 2, 3, right? And 6 methyl. 1, 2, 3, 4, 5, 6. Agreed? What about the Z? Which double bond can be E or Z? Can this double bond be E or Z?
No.
No, it has 2 hydrogens. Can't
Uh-huh.
be. So there's only one stereo stereo
that's a
center,
good
so
one.
to speak, or something that has stereochemistry. There's only one, so we have only one. But if there were more, let's say, for example, I'm just making something up. Let's say it was actually nonene, then that should also have E or Z. Then I have to include both.
Yeah.
Make sense? Is that the question? you were
That's
asking
exactly
about?
the question. That's a great.
Now, is that Z? What I have drawn, is that Z because it should be Z?
Yes, yes.
Okay, cool. You're done.
Nice.
Everybody okay? Cool. Let's talk about synthesis of alkynes. What are the best ways of making alkynes? And then we'll talk about reactions of alkynes.
What's today? February
Feb 20.
24?
No, yeah.
Okay. There is really only one way to make alkynes, and that is through a double E2, doing E2 twice. So the only one way of making an alkyne starts, it can either start with, it can either start with a vicinal dihalide, which you've seen before. Right? Have we seen vicinal dihalides before? What do we get vicinal dihalide from? Where does that come from?
Are you talking about the word or the what?
Where does this, what can I use to make this from?
X2 and
What's the
It's
thing
called
I start with?
Alkene.
Alkene. Alkenes can be used to create those, isn't that right?
yep.
Of course, in this case, the example has hydrogens on it. And what am I going to add as a reagent? Halogen with a
With an aprotic solvent.
aprotic solvent, right? So an alkene can be converted into that, isn't that right? We've seen that before. So vicinal dihalide can go through 2 E2s. One E2 gives us 1 pi bond, right?
Yep.
Another E2 will give us another pi bond. 2 pi bonds, alkynes. So doing a sequence of 2 elimination reactions, we can create an alkyne. But then the question is, what base should we use? Can somebody remind me what bases did we use in dehydrohalogenation to make an alkene? Yes. What base did we use to dehydrohalogenate and create an alkene?
Oh, it was H2 and no? And PD, no?
CO2 or NBS.
To make an alkene. What reagent base is used to dehydrohalogenate, which means eliminate HX? What is used here?
Alkoxide.
It has R minus?
RO.
RO minus.
RO
With
minus.
heat, of course. Alkoxide, a small base, Zaitsev's product, bulky base, Hoffman product. Does that ring a bell?
Yep.
But here's the thing though, it stops here. We want 2 pi bonds. Not just one, we want 2 pi bonds. That means this base is too weak for us. We can't use that base and get 2 pi bonds, which is what we need for an alkyne. So we have to use a much stronger base than an alkoxide ion. So a very strong base that is used for a double elimination reaction, removing 2 HXs to create an alkyne, and this is an amide ion. A very strong base, extremely strong base. So using sodium amide, for example, we can carry out 2 dehydrohalogenations and create an alkyne. Does that make sense, everybody?
Yep.
Now, it doesn't have to be a vicinal dihalide. Of course, vicinal dihalide we can get from an alkene. We can create that and then convert that into an alkyne. But it doesn't have to be a vicinal dihalide. It can also be, what's the opposite of vicinal?
Anti-vicinal.
No.
Sine.
Thank you. That's a good
Sine.
guess. Huh? What?
SYN, same side.
That same side. This is not same side. It's same atom.
Oh,
it's on
that's
the
true.
same carbon. It's not same side. I don't think I've used this word before, guys. It's probably a new word. It's called
Geminal.
geminal. Short
We used
form
it
is
somewhere.
gem.
We
Vicinal
used it
means on adjacent. X and X are on adjacent atoms. That's vicinal. Geminal means they're both on the same carbon atom. So similarly, you can also do a double elimination, 2 dehydrohalogenations. One is right here and one is right here to create 2 pi bonds using the same very strong base. We're not writing any mechanism here, we just need to know the reagents to be used. So for example,
Did you say no mechanism?
no,
I like those.
you like mechanisms?
No, without them. No, I do
Please
like
tell
that.
me what the product will be.
Write it.
Yeah, I'm going to write a couple more. Not ready for that yet. Okay, not ready for that yet. Not ready for that, so. Okay, yes, please, feel free. Come and draw it out.
What?
Okay, do you all agree? Yes? Basically, it's going through 2 eliminations. So that gives us 1 pi bond. And This gives us the second pi bond between those two carbons. Do you agree?
Okay.
Right?
Yep.
Let's do the second one then. That's multi-step. So,
Oh, do we show each step?
no. You can, that's totally up to you. Although it might not be a
I'm sure it's
bad.
the same product.
Same product from compared to, oh really? Yes it, yes it is. Yes it is. Didn't think.
You want me to write out the,
Please, yes, that would be great.
change it up a little bit?
Please, yes, please do. Dash it. It's scary when you're reading my mind like that. But yes.
That's what Hawaii does to someone.
Oh.
Rub it in. Go ahead, dude, rub it in.
Well, I'm gonna do that next
Go Hawaii.
quarter.
Was all of the Hawaii version and then we Sunita,
Yes.
there was also homework that you said you wanted us to remind you to go over. I don't know if you still wanna go over it, but
I would love to.
they're kind of similar to these questions.
Okay,
That's why I reminded you.
sure. Was it something that I wrote on the board or was it a handout?
It was something you assigned to
Can
us.
you give it to me and I will write a key and post? Because we really need to finish this chapter today. Do you guys all agree with what's on the board?
Mhm.
So when it comes to the multi-step, first step is giving us benzylic halogenation. Why do you have one hydrogen show up there? Guys, actually I've seen it, more than one person do this,
Oh,
which
whoops.
you have to be thoughtful about that. When you just write one hydrogen, you're implying there's only one hydrogen because you chose to show it. But if there's only one hydrogen and two bonds, should that be neutral?
No,
What should it be?
a carbocation.
So, but it's not, right? So there has to be another. So if you're choosing to write one, that's a little misleading. Either write both or don't write either. At least then there is no mistake in what you're trying to say. Excuse me, there's no misunderstanding in what you're trying to say.
No.
So, but anyways, coming to this though, first step is putting a bromine on the benzylic position, free radical, everybody good?
Yep.
And then there is an E2 reaction, Zaitsev's, agreed?
Yeah.
Then we are halogenating the alkene, making a vicinal dihalide,
Mhm.
and elimination again to make an alkyne. Everybody okay?
Uh-huh.
Cool. Let's try that one, and that's let's see what we get. So, oh, before I go there, I know I didn't highlight that information here, but how many E2s are happening from the dihalide to the alkynes?
Two E2s.
So how many equivalents of the base will be needed?
Two.
Agreed?
Yep.
Everybody understands that? Because each one equivalent creates one pi bond. Does one E2, so since we're doing two E2s, we need a minimum of two equivalents. Everybody following that?
Yep.
Yeah? Okay, cool. Let's try this. What will we get here?
1,2 dibromo butane.
Everybody agrees?
Yes.
Okay. Now, if I take two equivalents of that, what do you expect to get? Do you expect to get that?
No.
Right? Oh no?
Yeah.
Yes.
I would expect
I
to
would
do that.
have.
Yep.
What do you expect?
Yes.
Could another product be double bonds on both sides?
But the BRs are here. You're saying double bonds there? But the two BRs are here. That's your one E2, and then that's your second E2. The triple bond is between the carbons, well that's different. The triple bonds where? Is between the carbons that has the two CLs.
Here, I think is what she was saying.
Okay, what am I missing?
I think she was saying this bromine reacts with this hydrogen, this bromine reacts with this hydrogen, makes
What
two.
will that give you?
It won't work though. because
No,
it's two.
what
Two
will
H-
that give you?
2 HBRs.
No, not agreed, but that's not the focus. Our focus is the organic. Camilla, if that happened, so you're saying this goes and those goes.
Yeah.
What does that give you? Oops, sorry, does that give you an alkyne? 1, 2, 3, 4. 1, 2. Sunita, you can do this. It gives you two accumulated dienes. We'll talk about different kinds of dienes a few chapters down the road. These are called allenes, and these are not stable because of that very the stereochemistry at that central carbon is pretty strained. You have two orthogonal planes of double bonds. This pi bond and this pi bond are actually perpendicular to each other because of the orbitals that have to be used. So the point is, no, we are talking alkynes, so let's focus on alkynes. If that elimination were to happen, how do you get a triple bond there? You can't, right? So for the triple bond to be formed, the elimination has to happen where the two BRs are. But is this what we were expecting?
Yes.
Unfortunately, that won't happen yet. So let's pause. Alkynes are of two kinds. A terminal alkyne, which means the alkyne is at the end of the chain, or an internal alkyne. Alkyne, the triple bond is in the middle of the chain. Okay? Terminal alkynes at the end of the chain, internal alkynes in the middle of the chain. Now, terminal alkynes have something that the internal alkynes don't. Can someone tell me what is that? What is it that these guys have, but that doesn't?
No H
Where?
in the end.
Exactly. Why is that so important? Because the pKa of this H is about 25. Approximately. Which means if we have a strong enough base, this can act as an acid. And sodium amide is an extremely strong base. Very strong base. So the point is, if I take two equivalents of sodium amide, and as soon as even one of these guys is produced, what will happen immediately? Takes the proton, gives us the conjugate base.
Mm-hmm.
Make sense, everybody?
Mm-hmm.
So think about it, guys. Again, let's process this. Let's say I have 20 molecules of this. I'm just making up a number. I have 20 of these. I take 40 of those. Well, 20 of those react to make a terminal. But then, what about the negative charge? It's a mess. Can we pause? So, how many equivalents of sodium amide will be needed to create this anion? We need one sodium amide to do one elimination, right?
Yep.
Another sodium amide to do another elimination makes the terminal alkyne. But that terminal alkyne can't survive because this is decently acidic. So we need a third sodium amide to actually deprotonate it and make it a conjugate base. So minimum, how many equivalents of sodium amide used?
3.
Minimum. Or of course you can just take excess, lots of it. But then I don't want this, I want the neutral alkyne. So what should I do to convert this into neutral?
2.
What do I do to convert this into neutral alkyne? Add an acid. Exactly, that's a conjugate base. That is neutral because now there's an extra hydrogen there, which that doesn't have. So let's just add a dilute acid. Dilute acid puts the proton back where it belongs. Does that make sense, guys?
Yep.
So the problem is that terminal alkynes can be deprotonated, and this is an extremely strong base to do so, easily deprotonates a terminal alkyne. So we actually have to do this in 2 steps. First is elimination, but you have to use minimum of 3 equivalents or more, get the carb anion, and then that can be protonated by an acidic workup. You guys does that make sense, everybody? So, if that's the case, how do I convert please tell me steps I will need to follow so I can go from ethyl benzene to 1-phenylethyne. Now, internal alkyne, we don't have to worry about it because there are no acidic hydrogens. The triple bond is on the inside of the chain. There's no danger of a proton being taken away, so we don't have to worry about it. Terminal alkyne, we have to worry about it quite a lot.
Did you first add NBS?
Okay, if you add NBS, that puts a bromine on the benzylic position. Agreed?
Yep.
Please, guys, with NBS, don't forget heat or light. NBS is also free radical reaction, which means we need that energy source, heat or light. Okay, good. So you have basically put a bromine on the benzylic position. Okay, what next?
Ethyl oxide.
Second?
Ethyl oxide and heat.
Ethoxide. Okay, you're doing elimination with heat. So what does that give us? That gives us
The double bond.
what next?
No.
There's no halogen, there's no acidic hydrogen for
CO2,
NaNH2 to
CO2.
take. That's what you have. Sorry, say that again.
Br2, CH2Cl2.
Okay, so what are we getting at the end of that step? The alkene is converted into dibromide. Is
Yep.
that right? What are you going to do next? So now we have a vicinal dibromide. Now we can do
NaNH2.
elimination, right? So, what base are we going to use to do the
NaNH.
elimination?
NaNH2.
Okay, how much?
3.
Because mine is going there. What kind of an alkyne will that make? An internal alkyne or terminal alkyne? Terminal. So for terminal, you need at least 3, or you could have just used excess, meaning lots of it, but not less than 3. Then it will end up giving you a dirty mixture of products. Some reacted, some didn't react because there wasn't enough base in the system. We good, everybody?
Yep.
But here's the question. What will you have at the end of step number 4? Will you have the alkyne?
Carbocation.
You will have the what?
Carb anion.
You will have the carb anion. So how do I convert that into the alkyne?
Add H3O plus.
Dilute acid. That puts the proton back. Everybody's following that?
Yep.
But this is only for terminal alkynes. You don't really have to worry about it for internal alkynes. Terminal ones have an acidic hydrogen, internal ones don't. Everybody good? Questions? Okay, let's talk about reactions of alkynes. So that's really the only way to make an alkyne. Let's talk about reactions of alkyne. And actually the first one we've already talked about just now, and that is the acidity of the terminal alkynes. The hydrogen at the end of a terminal alkyne is decently acidic, and that's a very useful actually property for us to use in synthesis, as I'll give you examples. So the idea here is that if you have a terminal alkyne, this hydrogen right here is decently acidic, and with the use of amide ions, it can easily be deprotonated. By the way, can someone tell me what's the byproduct? What's the conjugate acid of amide?
Ammonia.
Exactly. Although we're not really interested in that. Now, why is this so important? Haven't you guys seen this before? Please tell me. Yes, lots of it. What have you seen it as? As a nucleophile. Very good nucleophile. What kind of reactions do good nucleophiles do? Absolutely. Absolutely. So for example, what will you get? By the way, this guy is going to become a friend very soon. This is ethine, of course. IUPAC name is ethine. Its common name is acetylene. It's a really good precursor for multi-step syntheses. Great place to start building these bigger molecules. So, FYI. But please notice it's really a terminal alkyne.
Mm-hmm.
Please tell me what the outcomes will be.
Do you want the mechanism?
No, not mechanism, just the result. I'll write one more. So once we deprotonate the terminal alkyne, it becomes a really good nucleophile and does SN2, not SN1. Good nucleophiles do SN2. Please remember that.
Yep.
Does SN2 reactions. Are we following this, guys? Is everybody following this?
Little behind, but getting there.
So, what's going on here? What's the first thing doing? Anyone? What's that doing?
Unprotonating it.
Deprotonating it. No. Agreed?
Yep.
Deprotonating. Fine.
And making it a good nucleophile.
Making it a good nucleophile. What's that doing in step 2? This is your SN2 reaction because you have a primary substrate, good nucleophile. So basically, this portion came from the terminal alkyne. that portion came from the electrophile. Are you guys seeing that?
Mhm.
But now this has two hydrogens. So we can replace both sequentially, one at a time. Does that make sense, everybody?
Yep.
We good with this? Sure?
Yep.
Okay, so what's the result after step 2? That takes one of the protons, SN2. Do you agree that that's your first step?
Yep.
And then deprotonate again, and then put the other electrophile. So this portion came from acetylene. Those two carbons with the triple bond came from here, right here. And then we added one electrophile and we added another electrophile. Make sense, everybody?
Yep.
So couldn't in the first step, could it remove both?
No, that's a good question. Generally in OChem, we don't see the formations of di-anions or di-cations, and so we just see one at a time. So you kind of have to do it sequentially.
Okay.
Yeah. Yes, Carrie.
I don't understand.
Which part?
Um,
This is a base that takes a proton from the terminal carbon.
yeah, the
Right?
acetylene. I don't understand.
In this one. Okay. So let's do it sequentially. Sequentially. What's going to happen with sodium amide? Step number 1. This is a base.
Take the hydrogen.
It's taking a proton. If it's taking a proton, it's becoming this. Don't care about sodium. Agreed?
Yep.
That's step number 1. Is that okay?
Yep.
Now that is a good nucleophile. If it's a good nucleophile, it does SN2. Remember OTS being a great leaving group?
Yes.
So, and that's primary. Can do SN2. Here's your nucleophile, here's your electrophile. So, substitute. Agreed?
Yep.
Everybody okay? So, what does that give us? That comes from here. We have now added, with me?
Yep.
Okay.
But that's also terminal, which means it can also be deprotonated with another equivalent of the base. Isn't that right?
Yep.
So, is that okay so far?
Yep.
Now that's also a good nucleophile. All of those are. So, in the last step, we are taking, going 2 down. Can I just go this side? So now, another primary substrate, which can do SN2, good leaving group, good nucleophile, does NSN2. That's the product. So the point is, very sequentially and very strategically, remove a hydrogen, a proton, put an electrophile through SN2. Remove the other proton, put the other electrophile through SN2. That's what we're kind of doing. Make sense?
Yeah.
Please go ahead. The last one over there. Please tell me what would be the outcome. Let's do this quickly.
Dash. Oh, there you go. There's right.
Oh, it's right.
So could you show the steps, the outcome of each step
Okay, yeah.
also?
Sure.
So these are mainly when there's terminal.
This is only because then they have the hydrogen.
Yeah.
Otherwise, the internal ones don't have a hydrogen,
So,
acidic hydrogen for the base.
so we can't do
You can't do it.
nothing.
Exactly. Well, at least you can't do that.
Okay.
Nothing, I mean, there's other things you can do,
Okay.
just not that. Okay, do you all agree? So first step is dehydration to make an alkene. Agreed?
Yep.
Second step is halogenation. You got vicinal dihalide, which we did elimination, but notice how there was no H3O plus. If there was no H3O plus after step 3, you will end up with the anion, which is a good nucleophile. So when you do step 4, it just gives us directly the SN2 product. Everybody okay?
Yep.
Questions? Okay, next reaction of alkynes is reduction reactions. Alkynes can be reduced. And you've seen a couple of those already in the previous chapter, but let's summarize it. Alkynes can be reduced in 3 different ways with 3 different outcomes. Alkynes can, please tell me what is the outcome if it is reduced with hydrogen and Lindlar's catalyst? Cis what?
Cisalkene.
Cisalkene, exactly. Produces cisalkene. Right? As we saw in the last chapter. We can also do a dissolving metal catalyst which uses sodium or lithium. Choose one, you don't have to give both, in liquid ammonia. What's the outcome there? Transalkene. So these two we've already seen because basically that's a way of making an alkene from an alkyne. But there's a third way of also reducing an alkyne which just uses hydrogen, generally excess, but at least 2 equivalents or more, with either palladium or platinum or nickel. Which means we are reducing all the pi bonds. What do you think the outcome will be? Anybody?
An alkane.
Exactly. It's a complete reduction. All the pi bonds are hydrogenated, ending up with an alkane. So 3 different ways, 3 different things we can do with alkynes. So let's try this. carbon.
So,
What? What?
am I even on the right track?
Nope.
No. Okay.
You missed step 3. I mean, I think you were on the right track till step 2, then 3 is where you took a detour.
Oh, do you want stereochemistry?
Not really.
Oh wait, do I not have this number?
3, number 3. I think that's where you got,
Let me take a look.
yeah.
Can I try?
Yeah, please.
Oh, fine, try it. Is that what I wrote on my paper?
So let's go over it. Is that okay?
Mhm.
What's happening after step 1? What do you have? What do we have after step 1?
Bromine
Mayor.
on the tertiary benzoic position.
Do you all agree?
Yeah.
What's the outcome after step 2? Please notice the base.
T-butoxide.
Is it exactly? Is it small or bulky?
Bulky.
Big.
So will it do Hoffman or Zaitsev?
Hoffman.
So what's the major product?
Number 1.
Agreed?
Ooh.
Everybody with me? What about step 3? What's giving us after step 3? What's giving us? That didn't make any sense. What do we have after step 3? Sorry, what were you saying, Jane?
I said anti-Markov.
Exactly, peroxide. HBr with peroxide is now a free radical mechanism which gives us the anti-Markovnikov hydrobromination. Do you all remember that?
Yep.
We should be able to write that mechanism too, guys. It's a free radical mechanism. So that's where you were. It's if we didn't have this, then you would have been right till then. But then we are stuck. Can't do anything with that because that's a tertiary substrate. Everybody okay? And then what's happening in step number 4? SN2, exactly. You've got, please notice, you have a nucleophile here, you've got a leaving group, SN2 gives us that. Does that make sense?
Yep.
One of the things that one of the skills, I guess, if that's the right word I'm looking for, or habits, is to account for pieces of your molecule. Notice that this portion comes from right here. Isn't that right?
Yep.
And that piece is right. Starting to see how they're connecting with each other. Now that alkyne and then the 3 reductions. So what are the products after each of those? Everybody's okay with this, right?
Yep.
The reaction numbers are going to increase because it's like reaction after reaction after reaction. So we kind of, as I was saying the other day, you got to have a good way of keeping that stuff organized so that at a moment's notice you're like, oh yep, I can do this, or no, maybe that reaction would work. So got to have that mechanism. So please feel free, don't hesitate, Jane.
Okay.
You're like on the edge of your seat right now.
I didn't want to hog the whiteboard, but Dash always does, so.
Oh, whatever.
Exactly.
No, that's the thanks I get.
Now watch me.
1, 2, 3, 4. So that's complete hydrogenation, complete reduction to an alkane, and this is cis product, right? And 1, 2, 3, 4, and the other is the trans product. Yep. Exactly. Is everybody okay? Make sense? Yes? Now if you're wondering how does everybody remember, guys, there's only one right answer for that. And what's that one word answer? Practice. There is no
Practice.
other way. There's no way you can memorize this stuff. Memorization will not work. Yes, Gary.
So for the H2 and palladium,
Yes, palladium.
palladium,
That's a D.
why is there no alcohol?
Because we are using excess of hydrogen, all the pi bonds get reduced.
Reduction.
The pi bonds can't survive. That's a pretty strong catalyst. This is really a poisoned catalyst. Poisoned catalyst means its catalytic ability has been reduced, so it can't go further.
The excess H2 takes.
Doesn't matter. Even if I use excess H2 here, because of this, it cannot go beyond that. It will stop right there. Even if I had excess of H2. So it's really the catalyst which is causing it to either go complete reduction or partial reduction, because it's a weakened catalyst compared to that. Anybody else? Okay, what about that? Please, let's do that one quickly. Please tell me what reagents will we use to complete all those steps. Anyone?
Top
Just
one.
go write it, please.
Mhm.
Just go write it.
No.
What happened?
Someone give up.
Why? You just got up. Carter, I thought you were going to just go write it. Oh, yeah.
Okay. Where am I also going?
Thank you so much. Can I eat that?
Yeah, sure. Palladium, platinum, nickel, any of those is good. Okay, what else? Yeah.
I can do that.
Do you all agree? Yes?
Wait, what does it say there? Oh, NA?
Yeah,
It's a negative positive, right?
just ionic.
This carbon is negative, so that's a good nucleophile. SN1, excuse me, SN2.
Do we need to put NA?
Yeah, or something.
No, you could have just written it like that, which is fine as well. Yeah. Everybody okay with that? Yes? Let's talk about the next reaction. This one is actually quite important. Not to say that the others weren't important, but this one is definitely more quite important. Hydration. What is hydration, anybody?
Adding hydrogen.
No.
Oh, adding equivalent to water.
So, what happens when alkenes are hydrated? What's the product?
OH.
An alcohol?
An alcohol. And of course, there are three ways of doing so, right? Depending on which method you use, you get that outcome. Now, alkynes can also be hydrated, meaning we can add water to, and I'm going to intentionally choose a terminal alkyne to illustrate this, can also be hydrated in two ways. One is kind of acid catalyzed, because yes, we are adding water with sulfuric acid and mercuric sulfate, all of those together. The other is, which may be more familiar to you, using borane or diborane followed by if you're doing hydration with an acid, should it go Markov-Nikov or anti-Markov-Nikov? Agreed?
Mm-hmm.
Can someone tell me what will be the product? Just go ahead, draw it out. If this were hydrated in a Markov-Nikov manner.
That would be.
What are we adding? We are adding water. Isn't that right?
Yep.
Which carbon would the OH go to and which carbon would the H be on?
Most substituted.
So which one? So the OH will go here, agree?
Yeah.
And H on the other, agree?
Mhm.
The other one, do you think that's Markovnikov or anti-Markovnikov?
Anti-Markovnikov.
That's anti-Markovnikov. Can you go ahead and draw the expected product?
To the less substitute.
So, what will this carbon have?
A double.
Hydrogen or
A hydrogen.
OH?
A
Hydrogen.
And what will the other carbon have?
OH.
You guys with me?
Mhm.
Now, these compounds that are drawn here are called, guess what? Ene, because there is a double bond.
Mhm.
All, because there's OH on the double bond.
Oh.
Enol. They are highly unstable. They do not survive, especially when you have an acid in the system or the base in the system. Under acidic and under basic conditions, this is not the final product because the enols typically are not very stable. They undergo a process, it's an equilibrium process called tautomerism. We will write a mechanism for the tautomerism part.
Well, that was the last question of the lab, but that you said not to do.
Or was there a question?
Well, you
about-
said not to do it, yeah. Not eight.
Okay, I don't remember, but that's okay. So yes, enols don't survive because they are not very stable under acidic or under basic conditions. They undergo tautomerism. May I show you how, and then we can talk about, we'll write a mechanism. So originally there was already a hydrogen on it, so one hydrogen there and wrong. Okay. It undergoes tautomerism. Please follow the bonds and how they are changing. That one becomes a ketone. Oh, wrong. My color coordination didn't work. That didn't work. It should have been this. That should be orange. Becomes a ketone. Double bond is moving. Hydrogen is also moving. It's not resonance because an atom moved as well. It is called tautomerism. And here, if we do the same, so again, I got my colors mixed up. It should be this, that is orange. That should be that. So undergoes becomes an aldehyde. The Markovnikov enol becomes a ketone. The anti-Markovnikov enol becomes an aldehyde. These are called the ketoforms. So the enol form becomes a keto form. Therefore, this equilibrium is called keto-enol tautomerism. Keto-enol tautomerism, where the keto form and the enol form are in equilibrium with each other. However, the keto form is more stable. The keto form is the preferred form. The enol form is the minor form. This process is catalyzed both by an acid and a base, or a base. Can be catalyzed under both conditions. So let's write a mechanism that explains how the enol form can become a keto form under acidic conditions and under basic conditions. So acid catalyzed keto-enol tautomerism. So let's take that example. So we have the enol already, right?
Yep.
Through a Markovnikov hydration of an alkyne. But Under acidic conditions, the double bond gets protonated. If the double bond gets protonated, can someone tell me what will it create? We've done this before in other mechanism.
Carbocation.
Carbocation. How many carbocations can this make? 2. What are those 2 going to be? 1 or 2?
Tertiary.
Agreed? Which of those carbocations, in your opinion, is the more stable one?
The one on the right.
Sorry, one more time?
The tertiary.
Tertiary.
Why? Is it just because it's tertiary?
Comes from the more stable.
But it's also resonance stabilized. It's not just, yes, it is tertiary, absolutely, at least in this example, but it's also resonance stabilized. You guys see the resonance structure? Yes? Let's go and
Yep.
draw the resonance structure. Where is the resonance coming from?
No oxygen.
Exactly. So the resonance structure of that agreed?
Yep.
What does that resonance structure need to do to become a
Neutralize.
ketone? Sorry?
Deprotonate?
Who's going to take, see, if I started with hydronium, I should create the hydronium because it's catalyzed.
So water.
So then the water is going to come, take the proton, give us the ketone, and catalyst back. So please notice, double bond got protonated first. It made the more stable carbocation, which is resonance stabilized, and the resonance structure needs to deprotonate to give us the keto form. The keto form is the more stable form. The enol forms typically are not stable. They can't survive. By the way, this happens in your biochemical systems all the time because your biochemical physiological systems are slightly acidic. So sugars constantly are doing this because they exist in slightly acidic conditions, so they're constantly going through the tautomerizations. Does that sound okay, everybody?
Yep.
Let's talk about the base catalyzed process. The base catalyzed process, ketoenol tautomerism. Please make sure you know how to write these mechanisms. All mechanisms we work on, you should know. If mechanisms we don't actually work on in class, you don't have to know. Okay, starting with the anti-Markovnikov starting with the anti-Markovnikov enol, which is under basic conditions, so that's why I'm using that as the example. What does a base do? Anybody? Takes a proton, which is the most acidic hydrogen in the system. And if it takes that, what does it become? And what is so special about this anion?
Electron rich.
What is so special about this anion?
Oh, sorry.
Okay, so what?
The resonance.
Exactly. It's resonance stabilized.
Oh.
It is allylic position, it's resonance stabilized. And if you draw its resonance structure, this is its resonance structure. Isn't that right? Everybody? And what does that have to do to become neutral? And where is the proton going to come from? Exactly. Because it's the base is the catalyst. If you're going to use a catalyst, you must reproduce it. So this is where hydroxide gets created again. So please notice the mechanisms are very intuitive in the sense that the acid protonates the double bond, makes a resonance stabilized carbocation, which then deprotonates to give us a ketone. The base deprotonates the alcohol, makes a resonance stabilized anion, which takes a proton from water, gives us the aldehyde. So this is ketoenol tautomerism. We must be able to write the mechanisms for the both. Everybody okay? So let's try this.
type.
Okay. So what do you think is happening after step 2? What's happening in step 1 of that reaction?
An alkyne is being formed.
There's already an alkyne.
Has a negative charge.
Say that one more time.
Has a negative charge.
Why does it have a negative charge? Who's the it? First of all, let's be very, very clear and specific in our vocabulary. When you say it, who's the it? Who has the negative charge?
Fi?
Sorry?
Fi? That's a negative charge. Right?
So, are you trying to say, Carrie, that this has a negative charge or something else? You've got to be very specific in your vocabulary. So what's happening in step number 1?
We're making a
The
carbon
base, yes, the base is doing what?
Taking a proton.
And therefore making a carbon. Is that what you meant? Yeah, good. But let's speak very clearly. The more clear you speak, the more clear your ideas, thoughts will be. Perfect. Okay, so what do you think is happening in step 2 then? Once you've created this, what is that doing?
SN2.
SN2. Isn't that right?
Yep.
So what's the outcome after step 2? Do you all agree that the outcome after step 2 is 1, 2, 1, 2, and then connected to that? Is everybody good? Yes? Okay. Now, what's happening in this? So, my arrow is totally, I think you get the point, right?
Yeah.
So when this alkyne is treated with those reagents, what's the outcome? Is that Markovnikov's, anti-Markovnikov's?
And
Markov.
Markovnikov.
So what will give us, what product would we get?
Well, the most substituted would
But
go
what?
to. I'm just processing.
Everybody needs to process it.
To the.
Would there be a tertiary alcohol on the cyclochrome?
Tertiary alcohol on no, not at all. Not at all. It's reacting with the triple bond, not the sp3 carbon. It's reacting with the triple bond. It's adding water across the triple bond in a Markovnikov manner, right? So if it's adding it across Markovnikov 1, 2, 3, 4, 1, 2, 3, 4, where is the OH going? Do you guys agree OH is going here?
Yeah.
And the double bond remains? One pi bond is used, but the other one remains. But can this exist? Can this survive? It's an enol.
No.
We just wrote a mechanism for ketoenol tautomerism. It's an enols. Can enol survive? No. What is this going to do immediately? It's undergoing tautomerism to produce what? Is it going to make a ketone or an aldehyde?
A ketone.
Because notice how the oxygen is on the inner carbon. It's going to make a ketone. Isn't that right?
Yep.
So what's the final product? That's your final product. If you're wondering where are the hydrogens from water, we added water. Well, two of these hydrogens are from H2O. This oxygen is from H2O. The third hydrogen, of course, was the original hydrogen that already was there. So that's the final product. Everybody with me? Is that too far away, Tanya? Okay, I'll try not to come here. I'll move over there next. Please understand, this mechanism we should be able to write. The tautomerism mechanism is what we wrote earlier. We should be able to write, once we get the enol, how does the enol become a ketone? But does everybody agree with me? Okay, what about this? Is that Markovnikov, anti-Markovnikov?
Anti.
Markovnikov.
Okay, I'm going to move to the other side, so hopefully Tanya can see better. I know it is too far, plus this color is not the best color. That's anti-Markovnikov. So if it's anti-Markovnikov, let's first write the enol. What would the enol be? Oh, what? Blue.
It's
Basically blue. I think it's Steve who just puts whichever cartridge in whichever.
Oh. With an aldehyde.
Exactly, yeah. 1, 2, 3, 4. That's the enol you would get, right?
Yes.
But enols don't survive, guys. Enols are very unstable, so when this undergoes tautomerism, it will give us an aldehyde. 4 carbons. Absolutely right. Markovnikov product gives us a ketone. Anti-Markovnikov product gives us an aldehyde.
What makes it survive the?
What do you mean? What makes it survive?
Yeah, because you said it doesn't survive there.
Enols are not stable.
So it just.
Why? Because
It's just a phase or just
It's
nothing.
say it again.
No, I was
No, I didn't catch the last part.
phase. I said, is that just
Phase.
like if it doesn't survive?
It's cause, and I know this answer is probably not going to be the best answer. It's just because this is just not very stable. It can't live.
And it just passed to
Just
the.
like, yes, exactly. It just quickly transforms into that. I don't know if you remember from Gen Chem, carbonic acid, can it survive?
No.
Why? Nobody asked then. Why doesn't it survive? Well, because its energy, potential energy, compared to the potential energies of water and carbon dioxide is much higher, much less stable compared to that. So similarly, this is much less stable compared to its keto form, so the enol form quickly becomes the keto form. Yes?
So for the mechanisms,
Yes?
both of them,
Yes.
the mechanism is just showing how it's resonance stabilized. Am I getting that right?
We just wrote the mechanism. If you want me to go over the mechanism, I'll have to do it after class. Because we just wrote the mechanism of ketoenol tautomerism. Please practice that. Please use that. See if you can write that mechanism. And if you want to go over it again, we can definitely do it after class. But I needed to finish this chapter today. So Carrie, what's the word?
You're not cramming?
I can't think of a word.
Putting her off? Or
Sure,
moving
I don't
outside?
want to, but I'm also not dismissing your question. That's
Dismissing.
what I was looking. But I do need to go on. And yes, I can stay back after class and do that again if needed. Okay, do you all agree? So once again, bromination of the double bond, making a terminal alkyne. The terminal alkyne then becomes a ketone with Markovnikov hydration, aldehyde with anti-Markovnikov hydration, and then complete reduction to become an alkane. Everybody agrees with that?
Yep.
Everyone okay? Okay. Where's my blue pen? Someone, I can't find it.
There. I think you can do it.
What reaction was this? That one is red inside actually.
Oh.
It's very misleading.
Find the red one.
Yeah, right.
And there's no guarantee. Okay, let's go to the next one, please. Thank you.
Is this one?
Yeah, I just messed up. Thank you. Thank you. Okay. If you remember ozonolysis of alkenes, alkynes can also be ozonolized, but with a different outcome. And this is the interesting part.
Found it.
Oh, thank you.
It's 4.
4?
Wrong 4.
Oh. Ah. Happy? Was
Yep.
that 3?
Yeah.
Oh, okay. Alkynes can also be ozonolized, but with a different outcome. Can someone tell me what is the outcome when alkenes are ozonolized?
The alkene is cleaved, and wherever the
Yeah.
double, and where the double bond connected, there would be a double bond. Oh,
Yes, but what is the product? What do they create when you cleave and put a double bond O? What is it?
Two
result
products
in?
with a O.
Aldehyde or
Ketone.
ketone, depends on what was on the alkenes, right? So, so alkenes, when they ozonolize, they break that, right, that the molecule splits apart, makes either ketones or aldehydes. Is that right?
yep.
Alkynes also can be cleaved. But the result is not aldehydes or ketones, it is a carboxylic acid. So wherever the carbon-carbon triple bond was, becomes a carboxylic acid, and of course, there'll be 2 of them because there are 2 parts to it. Everybody with
So
me?
the triple bond was supposed to be.
The triple bond breaks apart. It's gone. Wherever there was a
Oh,
triple
I
bond,
see.
now
I see
there's
how
a
it's working. Yeah.
Okay? Everybody with me? Okay, so. Please tell me what the products will be. Okay. I feel like I'm rushing right now just because I need to finish this chapter today.
It's just one more?
So again,
Is it one more besides this? Or?
you mean one more what? Reaction?
Yeah.
Yeah, there is, but we can't get to that. So why don't I, and tomorrow's exam, right?
Yes.
Okay, let's stop here. Ozonolysis of alkynes, we'll bring it up on Wednesday again.
Okay.
Do some more examples again. So I don't want to give you more things to work on today when you have an exam tomorrow. So how about we stop here? We will start over, oxidative cleavage of alkynes. We'll start over again on Wednesday and do more examples, and then we have other examples to cover in alkynes as well. So we'll do that on Wednesday. And
Tomorrow's at 12 noon, right?
12:30.
I mean,
Oh, 12:20, sorry.
yeah.
Where? That's a good question. Where? Where did we meet last time? Oh, there was nobody here?
Yeah.
Okay, then let's just do that. If nobody is here, great. If there's somebody here, then I know that room will be empty as well. So we are not bringing the lab notebooks, right?
Yeah, on Wednesday, right?
Can I give it to
On the
you
next
tomorrow?
lap.
Oh, next
Next
month.
lap. Please, don't move it.
Oh, that's your notes? Oh, sure. You want to take it from upstairs then? And then give it to me again tomorrow, so I can grade it?
Sounds good.
Yeah, just meet me upstairs. Yeah.
I was ready to go over the question.